Good morning. Now you are familiar with covariant tensors, contravariant tensors, Christopher curvature tensor, Ricci tensor, covariant derivative. And with this strong mathematical background, now we can deal with the Einstein's formulation of the field equation. Actually, Einstein did not derive the field equation, but he formulated it from a number of considerations. In the mathematical formulation of physical laws, only those quantities which possess invariance properties can occur. These may be scalar, vectors, or in general tensors. Any other quantity not possessing these invariance properties just cannot occur in the mathematical representation of physical laws. For example, if you are considering the law of conservation of a linear momentum, if you are taking one coordinate system, let it be some s, and you are taking another coordinate system which is moving with a particular velocity with respect to the s frame, let it be s dash frame, then the law of conservation of, if you are observing some collision in the s frame and in s dash frame, then the law of conservation of momentum should be valid in both the frames. So the physical law should be invariant. For example, if you are considering the temperature of a body, it will be the same if you are measuring that particular temperature in S frame or S dash frame. So we can say that temperature is a zeroth rank tensor. But if you are measuring the wavelength of some light, but depending on the relative velocity of S and S dash, this wavelength can be blue shifted or red shifted. So you cannot say that the wavelength is a tensor quantity. So the tensors are an entity which is independent of the system of coordinates to which its component are referred. So according to the principle of covariance, the field equation must be a tensor equation. So the Einstein's field equation is in tensor form. The second assumption is the Poisson's law in gravitation, that is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square equal to 4 pi 0, where psi is the gravitational potential, rho is the density of matter distribution, and g is the Newton's gravitation constant. When you are arriving at a general field equation, actually this should be one of the special case of that general equation. That is, under some suitable conditions, your field equation should reduce to this form. So if the 10 metric functions of g mu nu of Einstein theory. So here g mu we know that g mu nu is the metric tensor of the Riemannian space. Since metric, g mu nu is symmetric. That is, we know that g mu nu is g mu rho is same as g rho mu. So when you are considering the matrix form, in order to maintain the symmetric form, the components here should be same as the components here. So if you are considering in the case of general theory of relativity, we are considering a 4-dimensional space. So there should be 4 rows and 4 columns for your metric. Okay. So since this particular metric is symmetric, only these 4 elements, 4 entries, and then 5, 6, 7, 8, 9, 10. Only 10 independent elements should be there for this particular metric tensor. So under suitable condition, your field equation should reduce to this particular form. So you have to make sure that the new law of gravitation must not contain higher derivatives of g mu rho than the second. If your equation contains higher derivatives, then it is not possible to reduce that particular equation to this form, because this equation you can see that here the maximum derivative is dou square. So your field equation should also contain an equation that can contain the metric tensor g mu rho, but it should not contain higher derivatives of g mu rho than the second. Then the Ricci tensor is an option, because the Ricci tensor R mu nu does not contain any higher derivatives of g mu rho than the second. So the left hand side of your field equation can be related to R mu nu in a suitable form. Okay, now the third assumption is, actually the right side of this Poisson's equation contains the density of matter distribution. So our field equation, in the case of in our field equation, we can relate the right side with the energy momentum tensor T mu nu. Now according to the special relativity, the conservation law in flat space time is dou T mu nu by dou x nu equal to 0. So this particular equation should be valid, this is a tensor quantity. So when you are considering a geodesic coordinate, the same equation should be valid there also. So but in the case of a geodesic coordinate system, we have already discussed the geodesic coordinate system. In the case of a geodesic coordinate system, when you take the covariant derivative of the metric tensor, its value will be 0. Also the crucible symbol of the second kind and first kind, that is the second kind gamma, alpha, beta, gamma will be 0. So what will be the value of T mu nu, that is the covariant derivative of the energy momentum tensor with respect to nu. First you have to take the ordinary derivative of this particular vector with respect to nu, that is dou T mu nu by dou nu. Then since it is a contravariant tensor, so the next term is positive plus, and then you can write T and gamma here. We can first consider the first index, that is mu. When you are taking mu, you can write mu and nu terms here, that is mu and nu, and there is no change for the second index nu. Now you have to add one more term, let it be alpha, then we can write it as nu alpha plus T gamma. Now we are considering the second term, that is nu. So you can fix nu and nu here. There is no change for the first index. Here you have to introduce a new index, let it be alpha, and here will be alpha. Now we have already seen that the value of dou T by dou x nu, that is T mu nu, its value is 0. Since we are considering it in a geodesic coordinates, the crucible symbol of the second kind is also 0, so its value will be 0. So this particular equation, it is a tensor equation. So it is holding, this particular equation holds good in a geodesic coordinate system, then it should be true in any other coordinate system. So this particular equation holds in a curved space time. So this is the next assumption. So we are going to relate the left side with the Ricci tensor and the right side with the energy momentum tensor. But while dealing with the energy momentum tensor, what we are seeing is that its covariant derivative is 0. Since the covariant derivative of T mu nu with respect to nu is 0, the value of T mu nu with respect to nu will be also 0. Now the fourth assumption is, what is the form of this particular Ricci tensor? When you are going to substitute the left hand side with Ricci tensor, you should remember some points, that is you are going to connect the right hand side with T mu nu. Actually its covariant derivative with respect to nu is 0. So when you are considering a particular term here, it is in terms of some Ricci tensor or mu nu. Whatever terms you are considering, no problem, but its covariant derivative with respect to nu should be 0. Because when you are considering an equation like A equal to B, both are tensors, when you are taking the covariant derivatives, the right hand side is B nu, and here it is also nu. Actually the right hand side is 0 because T mu nu with respect to nu is 0, then the left side also should be 0. So while you are giving an expression, it should be noted that its covariant derivative with respect to nu should be 0. So the option is R mu nu minus half G mu nu into R. Actually this is a Bianchi identity. You can easily prove this particular identity. That is when you are taking the covariant derivative of this particular term, its value is 0. Sometimes the Bianchi identity is expressed as some delta mu or mu nu minus half G mu nu R equal to 0. Actually this is the divergence of the tensor quantity. So some others would prefer to write this particular equation as G mu nu. Okay, So in that case, that is this particular value r mu nu minus half g mu nu r can be also written as g mu nu. Okay, this is the fourth assumption. That is, the left hand side should be in this particular form, because according to the B and G identity, its a covariant derivative is 0. So our conditions will be okay. So these four considerations inspired Einstein to write down the law of gravitation in the form r mu nu minus half g mu nu r equal to minus kt mu nu. Let it be equation number 1. So this is the Einstein's field equation. Here k is a constant. Now in the geodesic coordinate system, the covariant derivative of g mu nu or the with respect to nu, or the contravariant g mu nu with nu is 0. So actually we have written this particular equation using the Bianchi identity, because the value of r mu nu minus half g mu nu r, the covariant derivative of this particular quantity was 0. So I can add one more term here, that is r mu nu minus half g mu nu r plus some constant lambda into g mu nu. Its derivative, its covariant derivative will be 0, because this is a constant and this is a conjugate metric tensor, and in a geodesic coordinate system its covariant derivative is 0. So this particular quantity is 0. So you can easily modify this equation like that. Sometimes this field equation can be written in the form r mu nu minus half g mu nu r plus lambda g mu nu equal to minus kt mu nu. Okay. Now we can consider some special case of this equation 1. Let us consider that the gravitation in empty space due to some source. Then it is in the empty space means the right hand side is 0. So you can write this particular equation as r mu nu minus half g mu nu r equal to 0. Okay. Now you just multiply this particular equation with some g mu nu. What you will get is g mu nu r mu nu minus half g mu nu into r equal to 0. So we are using this particular contravariant metric tensor to rise indices, but here both the indices are same. We have seen in the case of Ricci tensor, when you multiply the Ricci tensor with the contravariant metric tensor, what you will get is the Ricci scalar r. So its value is r minus 1 by 2 into what is the value of g mu nu into g mu nu. So we have already seen that its value is equal to the dimension of the space. Since we are considering the 4-dimensional space, its value will be 4. So into 4 equal to 0. So it means r minus 2r equal to 0, or r equal to 0. And you can now substitute this particular value here. That is r equal to 0. So the equation becomes r mu nu equal to 0. So this is the gravitation Einstein's field equation for a for an empty space. Okay. Thank you.